Hey there, let me find my microphone, get a little closer to my face. Here we go. 3.6 curve sketching. Now, this section is why we don't actually need graphing calculators. You are now going to be human graphing calculators. I don't know why it wanted red all of a sudden, but here we go. So, curve sketching. So, we're going to start with important features. And for any graph, domain and range, right? We got to know that. X and Y intercepts, they help us find the structure. We'll want to find asymptotes, whether it's an infinite limit or a limit at infinity. Extrema, first derivative, min, max, increasing, decreasing. And concavity, concave up, concave down, points of inflection. We might even use the second derivative test to check our extrema. We'll see what's going on. I don't know why that's spelled wrong. It should probably have a comma. Where are we? There we go. So first of all, domain and range. You know that domain is the set of all possible inputs for a function, and the range is the set of all possible outputs. We've been working on those since we first started the functions, right, in pre-algebra. Intercepts. The x-intercept is the x value when y is equal to 0. And the y-intercept is the y value when x is equal to 0. So whichever intercept you're trying to solve for, set the opposite one equal to 0. As we're looking for asymptotes, right? The asymptotes, vertical asymptotes, take place where the denominator is 0. Why are we not scrolling well? Horizontal asymptotes, the limit as x approaches positive and negative infinity, right? It can only have 2 horizontal asymptotes, but it could have infinite vertical ones. And the vertical asymptotes, let me just write this down. The vertical asymptotes are always of the form x equals, or input variable. Maybe it's theta, maybe it's t, whatever. And these ones are always y equals. They're horizontal lines. Horizontal lines are y equals equations. Vertical asymptotes are vertical equations. They're the x equals or input equals equations. Make sure your asymptotes are always equations. And your intercepts are always points. Right? Make sure you have points for your intercepts, equations for your asymptotes. To find the extrema, we find the critical values of the first derivative. So we take the first derivative, find where it's 0, find where the derivative does not exist, check some endpoints if they are involved, right? If we have an interval. And then we can use the first or second derivative test to determine if it's a minimum, a maximum, or a non-extrema. Then we move on to the second derivative, and we take this very organized, and we're going to keep it in the same order. I'm going to go 1, 2, 3, 4, 5. 1, we'll talk about domain and range. 2, we'll talk about intercepts. 3, we'll talk about asymptotes. Notice that these are very, very pre-calculus. Extrema and concavity are very calculus. And these asymptotes right here in the middle, that's where our pre-calculus is strengthened by the calculus, right? We tell you some stuff that we hope you believe, and then we show you why in calculus. So it's really a build, and there's more that we could do if we keep going. But let's start here. All right, so we want to sketch the graph. That's our instructions. Sketch the graph. Here we go. So for number 1, the domain. We know that x cannot be 1. For the range, it looks to me like this range is going to take on all values. So I'm going to leave this one open for now. That's not number 2. Domain and range are the same level. All right, domain x cannot be 1. The range, let's hold off on that for a minute. Let's see what's going on here. The second thing we're going to do is intercepts. The x-intercept has a y value of 0. All right, 1 minus x. I was going to turn that into an x, wasn't I? Remember, when a fraction or a rational expression is set equal to 0, that's when the numerator is 0, because we're just going to multiply both sides by 1 minus x. And on the left, that'll be 0. So the x-intercept is at the point 0, 0. When x is equal to 0, that's when this fraction will be 0. My y-intercept happens to be 0 over 1 minus 0, which is also 0. So the x and y intercept is exactly the same. There's only one, and it happens to be at the origin. Okay, so number 3, asymptotes. We happen to know that x equals 1 is a vertical asymptote. It's excluded from the domain, right? We get a 0 in the denominator, and as x approaches 1, from either side, our limits are going to infinity, right? So an infinite limit as x approaches 1. And we also find that we have y equals -1 as a horizontal asymptote. Why? Because the limit as x approaches infinity of x over 1 minus x, leading coefficients. All right, so -1. And we ask ourselves, let me see, what would it be? Yeah, and that's true. See, if x goes to positive infinity, we'll have a positive numerator and a negative denominator. If x goes to negative infinity, we'll have a negative numerator and a positive denominator. So it's always going to -1. So this is all the pre-calculus stuff, right? You could have done all of this in pre-calculus. Number 3 is just strengthened a little bit by calculus. So now, let's do the derivative stuff. First derivative, y prime equals low d high minus high d low all over low squared. All right, little quotient rule for you. That's a 1 minus x plus x. And that, to me, looks like y prime equals 1 over 1 minus x all squared. Huh. Well, that's very interesting, because that tells me some very, very important stuff. First of all, y prime is never 0. Y prime does not exist at x equals 1. But more important, notice that 1 is always positive. Blah, blah, blah squared is always positive. Y prime is always positive. So f is always increasing. Oh, not always. It's actually always in this manner. Let me use an eraser here. It's increasing from negative infinity to 1, and again from 1 to infinity. It's not increasing at 1 because it doesn't exist at 1. So always where it's defined. All right, so on the entire interval with 1 taken out. So there are no critical numbers except at 1. But since the first derivative is always positive, always positive, it's always increasing. Increasing. All right, finish that part. That's weird, but that's real life functions. Second derivative, right? Derivative of the first. So we take low square. This is so not how I would do it. All right, here's how I would do it. I would rewrite y prime as 1 minus x to the -2. Right, it's just 1 over. So let's take that 1 minus x up to the numerator, and we change the sign of the exponent, because now when we take the second derivative, it's easier. Bring down the -2, leave the inside alone, subtract 1 from the exponent, multiply by the derivative of the inside. Here we have 2 negatives, so that'll be a positive. 1 or 2, because there's a 2 there, and I somehow can't multiply. 2 over 1 minus x to the third. Again, the second derivative is never 0. The second derivative, I suppose we could do an interval. We could test this here at 1. Because notice, this numerator is always positive. if I pick a number bigger than 1, say 50, 1 minus 50 is negative. A negative number cubed is negative, and so I know my second derivative is negative here, and so it's concave down. I have a big issue. I just realized what I was doing here. Let me fix it. I'm going to copy that and then delete it because it needs to be on a different page. There we go. I'll fix that other spacing later. Here we go. All right, so it's concave down there. Take any number. I'm going to use 0, not to scale. Any number less than 1, put it in the second derivative. Say 0. 1 cubed is 1. This is going to be positive, so this will be concave up. So we do have various intervals of concavity. From negative infinity to 1, it's concave up. And from 1 to infinity, this graph will be concave down. Notice at 1, right, our only critical number, because it's where the, where are we, is where the first derivative doesn't exist. It doesn't exist in the second derivative either. So we can draw this. All right, check it out. I'm going to draw one, and then we're going to take a look at Desmos, see how we did. All right, at x equals 1, we have a vertical asymptote. At y equals negative 1, we have a horizontal asymptote. All right, what else do we know? We happen to know we have an intercept at 0, 0. Let me see the domain, the range, the intercepts, vertical and horizontal asymptotes. So it's always increasing. We might need a few extra points. We don't have a lot of information really at all about what else is going on in the graph. So let's take the original function. Let's evaluate at negative 1. The original function, which is y. Find f at negative 1. We'll get negative 1 over 1 minus a negative 1. Negative 1 over 2 is a negative 1/2. And we could, I don't know, maybe find another value over there. Say negative 3. Negative 3 over 1 minus a negative 3. That's negative 3/4. All right. So it's increasing and it's concave. Oops, concave up. All right, we're going to erase both of those. Let's see if I could draw it for real. It's increasing and concave up. Always increasing, remember. So if I take a couple of points over here, maybe I'll look at 2 and 5. At 2, our function value is 2 over negative 1. So 2, negative 2. F of, I don't know, 5 maybe. That's 5 over negative 4. So I'm coming up, I'm increasing still, and I'm concave down. Now, you might be thinking, Tuesday, that's a pretty creative graph you got there. Check this out. Let's see. Oh, did some stuff over there. There we go. X divided by 1 minus x. Oh my goodness. Looks like my sound was on my phone. That's surprising. That's exactly what our graph looks like, right? It's exactly what our graph looks like. We have our 0, 0. We have an asymptote here at 1. And look, we never reached the y value of 1. It turns out that as we're finding this horizontal asymptote, I should have said negative 1 there. Wait. Yep, y equals negative 1. The y values never reach. And so we happen to know right here, because of this asymptote, y cannot be -1. Now, horizontal asymptotes are not always places where the range doesn't hit. All right, so don't just assume a horizontal asymptote is going to be, don't assume a horizontal asymptote is always going to define your range. There are functions where that's not possible. All right, we're going to do the exact same thing with our next problem. All right, now we want to find the graph. In order, we have the domain. Domain, we're looking at our denominator. We know that x cannot be plus or minus 2. All right, so already for the domain, like we have some interesting things going on. I'm going to put a big number line up here. So I know at -2 I have something happening, and at +2 I have something happening just because of the domain. My range, we'll get to in a minute. Second, my intercepts. The x-intercept. The x-intercept has a y value of 0. And when we set a rational expression equal to 0, multiply both sides by that denominator, and we solve for the numerator equal to 0. So an x-intercept at -1, I am going to silence my phone now because I didn't do that the first time. It's like my sound is never on and I somehow managed to turn my sound on. Weird. All right, so we found the x-intercept. Let's find the y-intercept. The y-intercept has an x value of 0. So 0 plus 1 over 0 squared minus 4. That's a -1/4. So we have 0, -1/4. At least we have 2 different points now, for we have 2 different intercepts. That's good. We can also find the asymptotes. The asymptotes. So if we have a vertical asymptote, that will be informed by our denominator. Notice that the denominator has factors of 2 and -2, and the numerator does not. Since we cannot cancel these out, these will not be wholes, they'll be asymptotes. You should check the limit as x approaches 2 from the left and from the right. The limit as x approaches -2 from the left and from the right, in order to verify. But that would take this 15-minute problem and make it a 20-minute problem. And for me, that's a problem. Okay, so these are our vertical asymptotes. And it looks like we're going to have a y equals 0 as a horizontal asymptote. I don't know why vertical asymptote's capitalized and horizontal's not, but the VA is always capitalized, and well, you'd very rarely capitalize it. Finding that asymptote, it's actually going to help us in this case, I think. You know what? I'm not ready to commit to that, in all honesty. So now let's look at our derivative. All right. The first derivative is low d high. I don't know why my 4s are getting that crossbar. I think I'm not picking up my pen enough. It's weird. It's not even ink. It's digital ink, and I still am sloppy. Low d high. So we didn't do that well at all. Low d high minus high d low all over low squared. Again, 4. All right, so we'll distribute, simplify. We have x squared minus 4 minus 2x squared minus 2x all over our denominator. And when we combine like terms, I really just said ucky. I'm sorry, I'm not feeling well. A minus x squared minus 2x minus 4 over x squared minus 4, all squared. Okay, now critical numbers happen where the derivative is 0 or the derivative does not exist. So y prime equals 0 when the numerator equals 0. I don't like it when there's a negative out in front. So I'm going to do multiply both sides by a -1. X squared plus 2x plus 4 equals 0. I don't believe I can solve that. Let's use quadratic formula. B squared minus 4ac. All right, so we have complex zeros. We're not worried about it. So the first derivative is never equal to 0 because that numerator is never 0. The first derivative does not exist at x values of plus and minus 2 for the same reason that the domain doesn't include plus and minus 2. So when it comes to my, I'm going to put these here. When it comes to my critical numbers, it's the same. There's not much going on, right? It doesn't look like there's any maximums or minimums if these are happening always at our asymptotes. Look at that. Still running out of paper for this one. This would be a 4-board problem. Okay, so we're going to do this. We're going to check this out. We're going to do test intervals, but I'm going to come back to that. While I'm at it, I want to find the second derivative. Second derivative. Derivative of the first. So we take low d high. Low d high minus high d low. Remember, derivative of low, we have to use our chain rule here. So we'll have 2x squared minus 4 times 2x. Cram that in there. Don't forget the derivative of the inside. And when I bring that power of 1 down, we subtract 1. We're good. All over the denominator squared. And squared squared makes the 4th power. All right. Like seriously, I'm going to cut this into 2 videos probably. 2 problems is about all we could do of curve sketching in the classroom. And so I'll probably limit to 2 in each of these videos just because our algebra is going nuts here. We want to simplify. Oh boy. Notice, I'm going to use a different color. Let's use the color red. Here we have an x squared minus 4. Here we have an x squared minus 4. And here we have an x squared minus 4. So we could factor that out of all of them. And what happens, let me make this super tiny, is it cancels this one out completely. It makes this to the power of 3. And it makes this to the power of 1. All right, so when we're simplifying, if we take that out, and that only happens at the second derivative when we're using quotient rule, second derivative will have some cancellation, first derivative generally won't. So now we have x, oops, I want to take it back up to a regular thickness here. X squared minus 4 times minus 2x minus 2. And I'm going to take this 2 and the 2x and call that a minus 4x times minus x squared minus 2x minus 4 all over x squared minus 4 to the 3rd power. We still have to simplify that numerator, but it's not going to be quite as bad because we have fewer factors to consider. My second derivative simplified is minus 2x cubed minus 2x cubed minus 2x squared plus 6x plus 8. I don't know why that would be a 6x. I'd probably call it an 8x. I'm fading fast, guys. It's another reason why I'm going to cut it after this one. Plus 8x. Okay. And then a positive 4x cubed a positive 8x, and a positive 16x. Oh, that's an 8x squared. I need you guys to tell me, hey, Tuesday, you did that wrong. Over the denominator. So our second derivative, still simplifying. Algebra is easy, or algebra is hard. Calculus is done. Calculus is easy. That's 2x squared. Right? 8x squared minus 2 is plus 6x squared. I don't know why I wrote a squared there. See? Decompensating quickly. An 8x and a 16x feels very much like 24x and 8 over x squared minus 4 to the third power. Wow! Wow, people, wow! Okay. So now we need to find critical numbers and intervals of concavity. Here's what I'm going to do. I'm going to graph this numerator. This problem's gotten so out of control already. So 2x to the third plus 6x squared plus 24x. Oh, never mind. I already know my answer. Plus 8. So if I want to know where... I did something wrong. Oh. I'm getting used to parentheses. If we graph this, we're really bummed. So we'll go to z square. It looks like there's only one real zero, and that real zero is at -3. This matters to us, right? Because we want to set the second derivative equal to 0. And the second derivative does not exist at x equal plus or minus 2. So we have a potential point of concavity at -3. And it turns out, I think that this is a single solution of the cubic. I think this is a cubic that has 2 complex solutions. We really would need to see more of this graph, say the top of it. X values, I don't care. Y max, let's go to 20. Woo! Okay, what's our y-intercept here? 0. No, what's our y-intercept here? I already found 1/4. I want second derivative. I don't care about the y-intercept. I'm so sorry, guys. Back it up, back it up. Okay, domain, range, x-intercept, y-intercept, asymptotes. Original function stuff, all in black. First derivative, we find that it's never 0, but it does not exist at -2 and at 2. We have some issues with concavity over here at -3, though. So what's going on? What do we got going on here? Let's do some test values. All right, so I got something dealing with -3 over here. So for my orange test values, all right, orange test values from -infinity to -2, from -2 to 2, and from 2 to infinity. Now I want to use a test value, and I'm going to test using green. For my colorblind students, I do apologize. So I want the first derivative at -5. So first derivative at -5, right? Any value to the left of -2. First derivative at -5. So I have -5 squared minus 2 times -5 minus 4 over -5 squared minus 4 squared. And remember, we only care about the sign. -5 squared is 25. So we'll have a -25 plus 10 minus 4, which is negative. Negative 5 squared is 25. 25 minus 4 is 21. 21 squared is positive. Negative divided by positive, this one's negative and decreasing. Pick any value between negative 2 and 2. I'm going to use 0. The first derivative at 0 is negative 4 over negative 4 squared. Right? If I put in 0 for x, 0, 0, I get a negative 4. 0, I get a negative 4 that's squared. So again, we have a negative divided by a positive, which is negative. So again, we're decreasing. So what's up with this? All right, we're decreasing twice in a row. Interesting. Let's take another value. Use 3, I guess. The derivative at 3 is negative 3 squared minus 2 times 3 minus 4. And this denominator is squared. It's always going to be positive. 3 squared is 9, so negative 9 minus 6 minus 4, that's negative over positive, and that's negative, and this one is also decreasing. So this graph is always decreasing, but how is that possible? How is that possible? Well, we also have some concavity issues, right? We have concavity where we want to look at the intervals from negative infinity to negative 3, and then from negative 3 to infinity. Okay, so for concavity, let's use a test value in our second derivative. Something less than negative 3, I'm going to use the negative 5 again. In our second derivative, ugly, 2 times negative 5 cubed plus 6 times negative 5 squared plus 24 times negative 5 plus 8 all over 21 to the third. Right, 25. Negative 5 squared is 25. 25 minus 1 is 20. 25 minus 4 is 21 cubed. That's going to be positive. Negative 75 times 2 is a negative 150. 25 times 6 is 150. 24 times a negative 5 is a negative 120 plus 8 negative over a positive. Concave down on the interval from negative infinity to negative 3. Interesting. Let's see, let's check the second derivative at 0. At 0, we'll have 8 over negative 4 cubed, which is also negative. This graph's always concave down. And you're asking yourself, much like I'm asking myself, what? How's that even possible? Let's take a look. Let's take this one out. Put the new one in. Oh, work smart, not hard, people. Copy that. Paste it here. Look at that. It's always decreasing. Always decreasing. Always decreasing. Let's move that out of the way. Not only is it always decreasing, I see my negative 1 comma 0 for my x-intercept. I see my 0, negative 1/4. You see, this is concave down. This is concave up, though. There looks like a change of concavity. That second derivative, we had some issues. This one's concave up. This one's concave down. So my second derivative was messed up, and I just didn't do it right. So I'm going to do it again, and I'll probably give you the fixed notes. Oh, no. I'll tell you what. I'll give you a second chance at any quiz if on Monday when we come back, you show me what I did wrong on this problem. You show me what I did wrong, and I will give you an attempt at a quiz, a reattempt. Then I realized I'm recording this, so I can't do that because I can't do that for others. That's only my class. Bummer. Talk to me. Okay. So we can find this graph, the -2 and 2 vertical asymptotes. We have y equals 0 as a horizontal asymptote. I just screwed up the second derivative somehow. And I'll be honest with you, at this point, I'm not willing to go back and fix it. I know exactly where it was. It was here somewhere. I know I messed up 2x squared, this negative, a minus 2x. I'm sure it's somewhere around here. I didn't add well. Minus x squared, minus 2, minus 4. No, I don't know. I'll have to go back and check it out so I know if you're right when you come tell me about it. All right, we have 3 problems to go. The beautiful thing is number 5 is easier, but I'm still going to wait and do this in a second video. Or, I'll do it in a second video. That's it for now. Thanks for listening to this rambling. I'm really sorry. We'll see you soon. Bye.